हाँ। मैं समझ गया।
Glad when you should tell disconnect.
ठीक है।
Morning, everyone, and a warm welcome to all the participants of this faculty development program on thermal characterization and advanced measurement techniques. I, Prabkaran Singh Jolly, a BTech undergraduate from the Mechanical Engineering Department, NIT Srinagar, am honored to be your host for today's event. First of all, I would like to express my gratitude to the organizers of this FDP, Professor Adnan Qayyum and Dr. Sheikh Shahid Salim, for their efforts in bringing together such an esteemed group of experts and participants from different parts of the country. I would also like to thank the AICTE ATAL Academy, New Delhi, for sponsoring this event and making it possible. We have successfully completed the online sessions from 13th March to 18th March, and today we are beginning with the offline sessions. The last few days have been filled with an insightful discussions and presentations on various aspects of thermal characterization and advanced measurement techniques. I am sure that the next few days will be equally enriching as we delve deeper into the practical aspects of these topics. Through this FDP, we aim to provide a platform for participants to learn and share their knowledge and experiences and to foster collaborations among academia, industry, research organizations. I am confident that this event will contribute towards enhancing the skills and knowledge of the participants and enable them to apply these techniques in their research and professional work. Once again, I would like to extend my warmest welcome to all the participants and I wish you all a fruitful and enjoyable learning experience. Now, I would like to call Professor Adnan Qayyum and Sheikh Shahid Salim to the dais for the felicitation ceremony. I would like to request Professor Adnan Qayyum to felicitate our director, Professor Rakesh Sehgal, with the memento. A huge round of applause. I would like to request Dr. Sheikh Shahid Salim to felicitate our registrar, Professor Kasir Bukhari. Thank you, sir. Now, I would like to call forward Professor Shamim Ahmed Lone, Dean Academic Affairs, to be felicitated by our director, Professor Rakesh Sehgal. I would also like to call Professor M. F. Fani, Dean Research and Consultancy, to be felicitated by Director Sir. I would like to call Professor G. A. Harmain, Dean Faculty Welfare, to be felicitated by Director Sir. Now I would like to call Professor Nazir Ahmed Sheikh, Dean Alumni and International Affairs, to be felicitated by Professor Kasir Bukhari, our Registrar. I would like to call forward Dr. J. A. Bhatt, Dean Planning and Development, to be felicitated by Professor Kasir Bukhari. I would like to call forward Professor Abdul Iman, Dean Students Welfare, to be felicitated by our Registrar, Professor Kasir Bukhari. I would like to call our coordinator of this program, Professor Adnan Qayyum, to be felicitated by Professor Shamim Ahmed Loan, Dean Academic Affairs. I would like to call our co-coordinator for the program, Professor Sheikh Shahid Salim, to be felicitated by Professor G. A. Herman, Dean Faculty Welfare. Thank you so much, everyone. Now, I would like to invite the head of Mechanical Engineering Department and the coordinator of this FDP, Professor Adnan Qayyum, to come forward and deliver his welcome address. Professor Adnan Qayyum is a well-known expert in the field of thermal engineering with more than 30 years of teaching and research experience. He has numerous publications to his credit, and his research work has been recognized and awarded by various national and international bodies. Professor Qayyum has been instrumental in organizing this FDP, and it is his vision and efforts that have made this event possible. I request sir to please come to the dais and share his thoughts on the progress of this FDP so far and his expectations from the upcoming sessions. Please join me in giving sir a warm welcome.
Respected Director Professor Rakesh Saide, Dean, Registrar Professor S.K. Bukhari, HODs, our esteemed experts, HOCs, colleagues, guests, participants, and their students, good morning. I, on behalf of Mechanical Engineering Department and the organizing committee, welcome you to the Faculty Development Program on Thermal Characterization and Advanced Measurement Techniques. This is a 2-week hybrid blended program with both online sessions and offline sessions. Online sessions of this FDP were from March 13 to 18. Have successfully completed the session. In the online sessions, we had 6 sessions with 1 session per day. Expert lectures were delivered by experts from IITs and NITs. On day 1, in the session 1, the expert lecture was delivered by Professor Andali Tagik. He discussed digital imaging and liquid crystal thermography and discussed principles with relevant application process techniques. On day 2, the expert lecture was delivered by Professor Manish Mishra from IIT Roorkee. He delivered his talk on one of the various challenges faced by heat exchangers and discussed operational and measurement techniques, strategies deployed for such issues. The third session was presented by Professor Amresh Dalal from IIT Guwahati. He delivered his talk on analysis uh, of heat transfer in fin tube heat exchangers using regular type water generator. In fact, Professor Dalal presented a CFD overview for evaluation of the potential of such flow control devices. In session 4, we had an expert lecture, and it was presented by Professor Banerjee of SVNIT Surat. So he delivered his talk on characterization of gas liquid type two-phase flows. So this finds application in transport of oil in petroleum refineries and provides a tremendous exposure to the participants having inclination to such endeavors. On day 5, we had a very exhaustive lecture by Professor Subhash Chandra. He's from NIT Jalandhar. He presented his talk on heat flux and temperature measurement in combustion chambers. And this provides a very excellent exposure on how we can take measurements in like in IC engines, combustion chambers, or gas turbines. So the last lecture was related to recent advances in solar energy. So the audience was exposed to how we can exploit this energy source of the future. All these online sessions were very exhaustive and comprehensive, and I'm sure that participants of this course and the audience comprising of our institute faculty and our students must have gained an excellent insight about the state of art of measurement and characterization techniques necessary for gauging the system performance. These sessions were followed by highly interactive discussions with the participants, and I'm hopeful that each participant was satisfied by the replies of the experts. All these sessions were streamed live on our Institute YouTube channel and are now available for offline viewing. So today, March 20, we are kickstarting the offline sessions of this FDP. In this offline mode, we are having more than 8 sessions and several hands-on lab demonstration and training sessions. So these offline sessions are on advanced measurement techniques for fatigue. This will be delivered by Professor J. Hagman today. So, so this will be followed in the afternoons an industrial visit to HPCL bottling plant in Pampur. So we have already just sorted this thing with those persons there. So tomorrow we are having very two important expert talks. In fact, they are mandatory for all ATAL FDP programs. So one is on National Education Policy 2020, and our Honorable Director has given his consent for this talk. And this is followed by another mandatory talk on Indian values and ethos, and this will include some discussion on classroom conduct and behavior. So again, tomorrow in the afternoons, we are having a couple of good lectures. One is on fluid film bearings, and another is on advanced manufacturing techniques for research. So this advanced manufacturing technique for research will give a feel to the students how they can just customize their measurement gadgets or tools or sensors for precise measurements. So on day third, we'll be having again very good lectures. One is by on interface heat conductance by Professor Anvi Karo. So he'll be joining us through Google Meet, and we are having all the facilities of just watching him and interacting with him in this high-tech room. And in the afternoons, we'll be having some discussion on nanofluids, how we synthesize and how we characterize those things. And it will be followed by a lab session in our central research facility of the institute. So on day four, we are having a very important lecture. It is 3D scanning for measurement of cavitation in AC wear turbines. In fact, I would like to tell you something about this facility. Already, Professor J. Hagman has developed a very comprehensive setup in our mechanical department related to this. And his student will be just demonstrating, and maybe sir will also just show you how we are doing some such measurements there. So this will be followed by a very important lecture related to energy assessment of biomass systems, and an experienced faculty from chemical engineering department will deliver this lecture. So in the afternoons on 4th day, we are having some lectures on how we can use hydrogen as a storage material. Okay, this is a day 4. So on last day of this FDP, we are having a discussion on how we can take temperature measurement using infrared thermography. So this will be delivered by a faculty from NIT Rourkela. Again, we are just connecting with him to Google Meet. So he'll be talking about infrared thermography. And this will be followed by a very important lecture on experimental fluid mechanics. So it is the speaker, his name is Dr. Deepak Sharma. He is regional manager of TSI, India. So he'll be talking about laser-based techniques, including LEV, EIV, how we can use these, how we can use them for fluid mechanics. So all the Google Meets will be streamed live in the site at home, and the participants can quite easily interact with the experts. So this was as far as the sessions are concerned. An important session in this MVP is devoted to article discussion. So we'll just try to see hone your writing skills if you need some paper. So in this MVP, we are having approximately 50 participants. So I have divided these 50 participants into 10 teams. Each team comprises of 5 participants. So these teams can choose a topic of their own and then give a brief presentation on some day which is given in that schedule. So that presentation will last for 5 minutes. So because, again, this is mandatory, because we have to submit this thing in the report that the participants have given a brief presentation. Okay. So on the last day also we'll be having some MCQ tests related to all these discussions. Again, this is quite important. Okay. Okay. Fine. Now, as this FDP is organized by Department of Mechanical Engineering, so the participants are encouraged to visit the various labs of our department. Our department is having state-of-art tribology center, which is number 1 in India He's the founder of that. We have advanced data investing lab, Dr. Herman, state part facilities we are having there. So we have advanced production lab and a SaaS hub, and he has procured that 5XS CNC machine. So you can just develop all those sensors, whatever you want to make, customize all your instruments there on that machine. And our lab is energy research lab. So you can take some thermal conductor image developments as far as solids and liquids are concerned. And besides this, I have planned a detailed visit, a very good visit to a central research facility of our institute. And Professor Mani has given me permission that I can just use this facility there. So the participants will have hands-on session on Raman spectroscopy, which Shahid Saab has done very good work on that thing. Same low meter, trigonometer, nanodetection machines, etc. So this is as part of the facilities which we are having here. I hope that this during this offline session, the participants will familiarize themselves with latest measurement and characterization techniques which are important for the conduct of quality research. Finally, I am confident that the conduct of such FDP will reinforce the actual role of faculty in institutes of research. Further, this will help the participant in establishing an excellent networking in their relevant field, and maybe in some cases will lay a strong foundation for collaborative works. Finally, I'm hopeful that the participants will have a nice and wonderful time here at NID Srinagar. May God bless you all. Thank you.
Thank you so much, sir. Now it is my privilege to invite our esteemed guest, Professor S.K. Bukhari, Registrar of NIT Srinagar, for his address. Professor Bukhari is a highly respected academician, and his contributions to the field of education are well known. As the registrar of our institute, he plays a vital role in the administration and development of NIT Srinagar. We are honored to have him grace this occasion with his presence and wisdom. Without further ado, I request Professor Bukhari to take the stage and deliver the address to the audience. Thank you.
Professor Rakesh Sehgal, Director NIT Srinagar. Professor Ahmed Wani, my mentor in team research and consultancy, NIT Srinagar. Professor Harmain, Team Faculty Welfare. Professor Shamim, Team Academic Affairs. Professor Liman, Team Students Welfare. Professor Javed Ahmed Bhatt, Team Planning and Development. Professor Nazir, Team Alumni and International Affairs. Heads of the departments, coordinators of this workshop, my young faculty colleagues, participants, and boys and girls. Very good morning to all of you. It gives me immense pleasure to welcome you all to this 2-week FDP on thermal characterization and advanced measurement techniques. Since I'm not from mechanical engineering, so I beg a pause. Which is this workshop is I'm told that this workshop is sponsored by AICTE. Faculty development programs are very essential for faculty to keep themselves abreast with the latest technologies and research. When we were in infancy of our careers, at that time there were no faculty development programs conducted around Jammu and Kashmir or in NIT Srinagar. We used to go to IITs to keep ourselves abreast with the latest research and technology. Since last 4 or 5 years, since Professor Sehgal took the charge of Director NIT Srinagar, we have grown and we have grown by leaps and bounds in every facet of academics. He has left no stone unturned in giving us chance to promote education and to excel in every field of research. I am very grateful to him.
In fact, we are.
I'm told that this is a 2 week faculty development program. 1 week is already over, that was conducted online, and this we are here for offline mode. And obviously, I'm sure that many facilities at NIT Srinagar have been developed, as Professor Adnan said, that Professor Wani has developed a number one lab in North India, and perhaps there are only such 5 labs in the whole of the country. You will have some chances to have hands-on certain experiments, and you will gain such experience. It will be beneficial for your teaching and research. At the same time, I am grateful to AICT for sponsoring this program. AICT is the academic body which always is at the forefront of technical education. Last but not the least, I must congratulate my two friends, Dr. Shahid Salim and Professor Adnan, for coordinators of this workshop, for organizing such a wonderful workshop for young participants in this project. I once again welcome you all to this faculty development program, and I'm sure that you'll gain a lot of experience in thermal engineering. Thank you.
Thank you so much, sir. We are now honored to have with us our esteemed chief guest for today's event, Director of NIT Srinagar, Professor Rakesh Sehgal, who has taken time out of his busy schedule to grace this occasion with his presence. It is an honor to have such a distinguished personality among us, who has contributed immensely to the academic field and has led NIT Srinagar to new heights of excellence. We are eagerly looking forward to hear from Professor Sehgal, who has always been a source of inspiration and guidance for all of us. We are grateful for your presence, sir, and I now request you to take the dais and address the audience.
I think I don't need this. Am I audible?
Actually, we are going live on YouTube.
Okay. Acknowledging the graceful presence of my senior colleagues on the dais, and my younger colleagues, the participants from different institutions, PhD students, faculty members. I welcome you all to this eventful morning. Good morning and adab to all. At the outset, I would like to congratulate Professor Adnan and Dr. Shahid Salim for choosing a very appropriate theme for this faculty development program. I was connected to few online lectures, not all, but I was, in the evening he used to send the link and I used to open and I used to be connected for some time. All the lectures delivered, at least I have attended 3 lectures, partially, they were all very wonderful. In fact, such FDPs sometimes, they decide the course of your research. And I'm sure that this is going to be true for, if not all, at least for some of you. Because I myself, I have been benefited by one such FDP, which was conducted by the ITMEC way back in 1997. I was there for 5 days FDP on reliability and maintenance. And during the course of that FDP,
I decided in which direction. I was MTech at that time, MTech from Delhi design. So I decided to pursue my research in that particular direction because I got interested. The deliberations, the lectures were so fascinating. They were so interesting that it inspired me to pursue my doctorate in that direction. And you will not believe I wrote the first draft of my first paper in those 5 days, which then later on it was published in ASME Journal of Travel. In fact, the techniques which they have chosen, thermal engineering is a very wide field. If we look at the earlier scenario of the research, maybe about 25, 30 years back, a little experimental work will give you, will award you, will make you eligible for the award of doctorate. Then during that period, certain computational techniques were developed. When you have to undertake research in the thermal phenomena, it's basically all flow processes, whether it's a heat flow or fluid flow or whatever flow, you need to focus on a particular area, and that needs discretization. Because either you have to go for finite difference techniques or finite element techniques. Now, finite difference techniques are, they are not that popular. Now, people are going for finite element techniques because of the obvious reason, because of the development in the field. And then side by side, you have many softwares which cater to the simulation of the phenomena and a kind of confirmation of your experimental results. You have softwares like ANSYS, you have softwares like Fluent, and all that. Because you are from this area, I am from design, so I don't know much about these things, but I too have used discretization technique in my research. And this becomes very involving and very interesting. You have to be very good at numerical techniques so that you can, really simulate those phenomena, that you can then convert those differential equations into algebraic equations and then finally arrive at the, because you need to ultimately, you can't just handle them directly. Of course, nowadays some of these like compilers like MATLAB and all, they will allow you to some extent to handle those variables, but otherwise it is difficult. In those days it was more difficult. So I'm sure that you will be definitely benefited by the lectures which were already held online, and now the lectures which will be held offline during these 5 days, and then your visit to various facilities. Professor Harman has developed very wonderful facilities in the area of structure mechanics. His lab is one of the best lab in the country. Believe me, I've not seen such elaborate things. Even you can't imagine an impact tester costing 50 lakh rupees. UTM, which will have a lot of, you can go up to very high temperature, probably 800, 900, 1100 degrees. That's really wonderful. A few crores of rupees. I think his lab was maybe not less than 5 to 6 crores worth of equipment. Similarly, Professor Wani has developed a very wonderful Central Research Facility Center. Of course, my other colleagues, Professor Shah has also been involved in that. And we have very wonderful facilities for characterization of development, characterization of materials and proteins. You can go up to nano level. I too try to involve myself sometimes. My colleagues are very generous. They allow me to enter their lab and sometimes interact with the research scholars. Now my job is full-time administration, but I'm because being academician for 36 years, I'm also interested sometimes to go and interact with the research scholars and other students. So the facilities are wonderful, the people are wonderful, the lectures were wonderful and will be wonderful during the next 5 days. So my suggestion is, please take maximum use of all these facilities, make maximum use of them, try to learn as much as possible. Probably that will make, for at least for few of you, that will make your targets for research much easier and much clearer. Because clarity is very important. You have to weigh, what is your strength. When I discussed about my research topic with my guide at IIT Delhi, he asked me first question, what are your strong points? In which area you are strong? I said I am a design engineer, because in my master's project I had worked on non-circular bearings, design and analysis of non-circular bearings. So I told him my strong area is bearings. So accordingly, then he suggested the problems in that direction. So it's always important to see the area in which you are strong, where you can contribute more. It will be much easier, instead of learning. Of course, it's always good to learn something new, but to start from zero is always difficult. So you may plan to start from a point up to which you know. So with these words, I once again congratulate the coordinators of this program and I acknowledge the support of all my colleagues for the successful organization of this faculty development program. I will feel myself lucky if at least a few of you, taking a clue from the deliberations here, decide and progress in your area of research. I wish you all the best. Thank you.
Thank you so much, sir. Ladies and gentlemen, it is now my pleasure to invite Dr. Sheikh Shahid Salim, the co-coordinator of this faculty development program and the head of the Department of Training and Placement of NIT Srinagar, to deliver the vote of thanks. Dr. Shahid has been instrumental in organizing this event, and we are grateful for his leadership and dedication in making this program a success. Please join me in welcoming Dr. Sheikh Shahid Salim on the stage.
Assalamu alaikum. Good morning to you. My privilege to be able to present this vote of thanks for this FDP, which is on thermal characterization and advanced measurement techniques. You have been there for the past week, joining us quite late in the evening. Not easy to have lectures at that time, that too online. So keeping, as I was looking at the interaction sessions that happened later on after the delivery of the lectures by the experts, so I could find really good questions being asked by the students, and it showed that yes, all of you were there, present, and actually listening to the lectures and getting benefited by them. So my privilege again to present the vote of thanks to the director, honorable director, Professor Rakesh Sehgal, and registrar, Professor Kaisar Bukhari, for all the administrative support that they provide to us throughout all the academic activities and other activities, and plus for this particular FTP. Thanks are due to all the deans who are present here for gracing this occasion, and the resource persons. You have been interacting with them, around 6 of them the past week, for the really insightful lectures, and to our departmental faculty and the support staff for supporting and coordinating these activities for this FDP. And not last and not least of all, to all the participants who are present here, to our students who are here listening to these lectures, and for gracing this occasion for the FDP. I hope this next week will also be really wonderful for you in terms of your learning. And as just the editor said, this FDP or any FDP that any student of any stream basically attends is basically a game changer for some where actually you actually look at the research part. So I think, as I said, if there are a few of you who will actually select some topics and actually go ahead in your research in this particular field, that will be really great. My thanks to the organizing team, that by Prakaran and Koshan Kari, for organizing the FTP. They were always with Professor Adnan at all the times, and even late. So I could see around Professor Adnan would lead around 10, 10:30 in the evening after finishing the lectures in the room. So again, thanks to AICT, ATAL Academy, for providing all the support and the monetary support for this FTP. So to Dean PND for providing high tech and all his staff who were there. Actually, it takes a lot of effort to run this particular high tech and also all the activities that happen here. Dr. Kadri for providing all the support for this transportation and everything else. To our undergrad and PG and research scholars for being there again with Professor Adnan. I could not do much because of I was really busy quite elsewhere, but he has been there and all the students have been there. To our social media cell for their time and effort. And to the participants, thank you once again. Hope you have a great time. We'll be having tea outside for the other participants. Do we have here? Okay, so okay. Thank you so much. Thank you for listening, and hopefully we'll have the next session after tea. Thank you.
Thank you so much, sir. Now I would like to inform all of you that we'll be taking a short tea break. Everyone is kindly requested to proceed just outside the high-tech hall. We will resume the program by 10:30 a.m. with a lecture by Professor G.A. Helmet. Thank you, everyone.
introduce him in the coincident. Once he was moving from after attending the lecture towards hostel, but his foot was bleeding. Somebody told him, Harman साहब, आपका तो ये पाँव से खून बह रहा है, इसको ये भी पता नहीं थी. और दूसरा चीज एक्चुअली इनको इनकी पब्लिकेशंस की he has worked in NIT also very hard. यहाँ पर तो it was not अगर आपको जिंदगी में कुछ हासिल करना है तो प्रोफेसर हरमैन की पब्लिकेशंस भी very high standard की है. You can see he has produced PhDs in NIT and he has lot of merit in his both in his heart and mind. So and the struggle which he has taken, he can become professor in any university of the world. I'm telling you, without any exaggeration. So with these words, I just again inform you that you must take full advantage of not.
Academics are very open. I know that how much struggle you had yourself to do to bring life to tribology in the institute. There was a time when we would be cherishing. And he is world recognized. Well, it is, I'm humbled and honored by his words. Bismillahirrahmanirrahim. Assalamu alaikum to all of you, and a very good morning. Adab, if that pleases you, namaskar, whatever pleases you. Please be very free to ask me whenever I'm either fast or I'm not understanding. You see, I was not. I have worked in thermal field. Uh,
if there were no dramatic failures in the world, there would not be better designs today. You see, civil engineers never thought about what should be the strength of concrete at 800 degrees Celsius if the World Trade Center type of disaster would not have occurred. Or if you look at space shuttle, that how a simple seal somewhere, which was not costing more than $20, has cost billions of dollars. Or if you look at certain types of failures, probably this occurred in 1984 in Japan, people have learned lessons from these failures. I have also put liberty ships. World War II witnessed at least 200 of liberty ships breaking into two parts and some of them failing and sinking completely. This was because people moved from riveted type of joints to the welded type of joints, and they did not know what to measure to see that the weldment is of an adequate quality. Okay, so measurements come into play, but what type of measurements you have to make is dictated by the type of the situation, the type of the parameters that you may be interested in. And this particular, incident is in particular responsible for shaping the way people will look at fracture mechanics. You will see that in France and in other countries, when the industrialization had begun, they did not have the concept of the thermal expansion of steel. And you will see that the railway lines used to become deformed altogether. And measurements again, how much it has deformed, how much allowance we have to keep for thermal contraction and its relaxation was not known at that time. Okay? Which one is to impress? So, herein I am telling that it is not necessary that there will be big items only wherein fracture and fatigue type of failures exist. A simple can that you have to open, if you do 2-3 times, to and fro motion to the point where the lid is to be opened, you will see that it will be back in your hand. So you find that some few cycles only are required to break it. And if this knowledge was not there, you would not be able to sip the the drill that you are interested in. Or, for example, the failures of gears or the failures of the bones, how the propagation occurs, and so on. These are some of the cases wherein measurements become very important as the passage of time goes by. I have herein tried to give you the historic failures and their impact on life assessment of the company. We are interested in having fail-safe type of a situation. Okay, we don't want to have a situation wherein there is no corrective action to be taken because time has already elapsed. So what is the design life of a company? You will see that a number of failures starting from 1842 to on this slide after 1944, you will see that Tacoma Bridge failure, probably you study it in vibration classes also. You will see, life assessment developments. What has finally been done by people to overcome such problems is also being written in the last column. I'm not going to go into the details of this because this will completely, shift the focus from the actual topic to the historical developments and the lessons that have been learned, as a consequence of occurrence of those failures. But I will have still some more. Herein I am forced to tell you about this particular case. one of the Comet aircrafts that failed. It flew from Kolkata airport in India, and disaster was within 20 minutes of flight. Another two failures occurred over Mediterranean, and Comet aircrafts were built by De Havilland Company of United Kingdom at the time, and it was a competitor with the Boeing. And if this failure had not occurred, or these failures had not occurred, you would have this time aircrafts from De Havilland Company as well. Instead, Airbus took up in France. They gained two, three companies gained out of this. Bombardier in Canada, it gained from such failures. But the question is, the wreckage was not, collected near Kolkata, but it was collected near Rome in Italy. Okay, and nothing was known why the failure should occur because all calculations were okay. Then what did they do? They took one full fuselage, full body of the aircraft in Georgia Institute of Technology, and they pressurized and depressurized it. And they found that there were cracks which were propagating from remarkably square cabin windows of that particular aircraft. Till then, people used to build the aircrafts with square cabin windows. This time we find that these are oval shaped, isn't it? So it has not been overnight that people have shifted to that kind of a design. And the fracture mechanics got another boost, from aircraft manufacturers. They employed many people to find out the causes of failures which occurred by fatigue. So there are other incidences wherein corrective actions have been accordingly taken, but you will see that particularly I have not written that here, that the creep, which occurs generally beyond 0.5 times melting temperature, was another problem, which was true for the nuclear industry in particular. And even if you are okay with fatigue type of design, you designed against fatigue very well, but because you are not adroit in terms of taking action against the creep, then there was creep and creep fatigue interaction which led to the failures of many items. And finally, this time the nuclear industry, the acid type of test for any of the items is that it has to pass the creep fatigue interaction. So there are others wherein we are trying to tell you that no, we have learned from the failures a lot, and new measurement techniques have also come up because of those kinds of failures. Now I've given you an exhaustive summary of some of the failures which have already occurred, and you will see that certain things are common. I would say that up till 1904, people did not have an idea that there can be localized plastic deformation in the material. And it was Ewing Humphrey in 1904 who gave that idea through optical microscopy. And they were convincingly putting aside what was called as recrystallization theory. And before that particular incident, there were theories which were propounded to tell about the cause of the failure. And they said, no, it is because of something else. And they gave the concept of persistent slip bands, PSBs. So this time you will find no book in fatigue probably written abroad or here will be skipping the idea of persistent slip bands. These have to be there if there have to be the propagating cracks present. And I will tell you, no book on fatigue will ever be written if there were no plastic deformation. This is a line that you will find in the book by Dept. There is a book on fatigue by Dept, and you will see that he writes that there will be no book written on fatigue if there were no plastic deformation. And because of this irreversibility of plastic deformation, you will see that the cracks start to emanate either from the surface. Why surface? Because if you look at the surface, the atoms on this part, they have no bonds on this side, so you can break them easily. While as if you go deep, they have neighbors on all the sides, and therefore very difficult to have the kind of you see crack propagation probability within the material. So that is why they generally propagate from the surfaces, though it is not the essential and the sufficient criteria for the cracks to propagate. Now we will see that what is the commonality of all the failures I have shown is that there is formation of crack. Now where is the measurement coming? How best you can tell about the existence of an initial flaw is the main Achilles heel for the purposes of determination of how fast the crack is going to grow. So what is happening is that you have, for example, dye penetrant tests, you have eddy current tests, you have certain other acoustic emission type of tests by which you will be able to tell about the existence of already existing flaw. And there are other invasive techniques, non-invasive techniques in which you will be having an idea about how much is the damage already with the material. And therefore you will find that this was the main cause. Then it is to be characterized by some. So we are characterizing it by the length of the crack, which is generally designated by small a in fracture mechanics. And what's happening is that you can have either what is called a stable type of a crack growth, or you can have unstable type of crack growth. And there are conditions. When will crack growth be unstable? Will be when the materials has got combination of stress and flaw size of such a nature that the stress intensity factor becomes equivalent to its fracture toughness. So if it has already become fracture toughness, then you will be having uncontrollable type of the crack growth, which is called unstable crack growth, and that also has to be characterized. How fast the crack is growing will be given by what is called as dA by dN. Capital N is the number of cycles. So if you know how much is the growth per number of cycles, you will have an idea about another parameter which becomes of paramount importance in fatigue. So you have then certain types of techniques to measure these quantities. You can measure them in lab, and this is what I will try to bring home to you in a very short and very precise way. Now, about the measurements, I wanted to make this talk more interesting so that you take something with you. If you look at pi, I have shown herein only first 1,000 digits. And do you know the Greek ancient philosophers, how they measured pi? They will make a circle of a rope in a big field, and then inscribe it within a square. They will wait for the hailstorm, and then they will count these number of hail particles within the circle and within the square, and proportionately find out the value of pi. So they reach to 3.14, probably 1. And the type of civilization you are living in is directly related to the type of measurements you do. If you go to Wikipedia today, okay, I had kept this ready for myself, and you go to pi, pi, you will see at one place he writes that the computations are motivated by developments of efficient algorithms, and they have reached to trillions of places of decimal in 2021. Trillion places of decimal. It is not like Archimedes' time when he could go to 7th place of decimal and it would be celebrated. So you know where we are today in technology, and it's directly related to the measurement. How can you do this kind of a measurement? So you have to know from that how it has evolved from Egyptians who could measure to only 2nd place of decimal and have get the pyramids which are standing the test of time. to the point where people have gone to the trillionth place of the more than trillion place of decimal by now. And you will see that herein I'm trying to tell that Euclidean geometry changed the way we are looking at the measurements today. All of us today are taking for granted a straight line is on another straight line. The sum total of these angles has to be 180 degrees. This is well known. However, imagine this thing being told in 300 BC or somewhere, okay, and how much it should be a hard work then. Now, I have also shown about the measurement. You will see this is Cheng Heng's seismoscope. There are four these what you call dragons who have got steel balls in their mouth. Suppose there's an earthquake of some magnitude, one ball will drop. We know that it has got this much intensity, and they will see the direction in which this ball has gone. Then know that the earthquake has come at such and such place. If two balls will fall, then its intensity is double. Three balls will fall, four balls. So this was happening in China long back. I mean, in some millennium BC, that they had this technology. And this is called as Chang Heng's seismoscope. You will find it anywhere in the net. Mr. Junaid Kazi, he downloaded some figures for me. I have given him the captions. And then you will see that how the, ancient Egyptians were, using measurements and geometry to construct things. They have not come of their own. It is by hard earned measurements that they have shipped the items. They knew about buoyancy. I hope that you know about Eureka. Eureka. Who told Eureka? Eureka. Because purity of gold was to be known. How pure the gold is. So measurements had to be done. Measurements always changes. So I have tried to tell you that this time, you can go to trillion places of decimal. So measurements are, being done sometimes directly, sometimes indirectly. And you will see, when we talk about structural integrity assessments, you know about Titanic failure. All of you probably have seen the movie, or you have the idea that there was a big ship which finally collided against an iceberg and broke. Why did it happen was because people did not know at the time about nil ductility transition temperature. You see, I have tried to show here. You see, this is 0.01% carbon steel. What are you seeing? This is a temperature. Unfortunately, it is an old figure. It is in degree Fahrenheit. Now, whatever is here, the temperature, you see, it is having an ability to absorb through that kind of a test, around 250 foot-pounds of energy. But if you go a little bit on this side of temperature, it can absorb only this much energy. This is what happened to that particular, ship. It was not able, you should have the ability to absorb the energy. But this material had no ability because it was minus 4 degrees Celsius at which that ship was wrecked by that particular, iceberg. And I hope you know that there was then a ship called Carpathia which was nearby, and it saved certain lives, but many lives were lost, and whole of that particular ship sank. But people have taken coupons of that material, they have analyzed them, and they have found that this was because of nil ductility transition temperature. You see, this temperature is called here for this material nil ductility transition temperature. That you have no ductility if you are on this side, you have ductility if you are on this side. This is observable for many of the materials. And this is again, which was possible by making some very sophisticated type of measurements. Now herein I'm trying to tell you about the same, item that was you see, Comet aircraft. But here we are trying to tell that now people have realized that we cannot live without defects. If I have to tell about defects, I should have probably 1 more hour to tell. But I will tell you the gist of the failures. You see, there was a Russian scientist, his name was Ayov. What IOF was doing, he was measuring the strength of sodium, chloride crystals. Some of those crystals fell by chance into his hot cup of coffee. He kept them aside. He said, now their strength will be less, so I should not confuse. So he kept them aside. Then he measured their strength. To his surprise, it was much more than the ones which had not fallen into the cup of coffee. Then what did he say? He said this by falling of these crystals into the cup of coffee, they got relieved of the wounds on them. The cracks were there, which were eliminated by their falling into cup of coffee. And therefore, the cracks and their influence on the strength was actually studied in a very different way. It was by accident that people realized that yes, cracks can indeed, you see, decrease the strength of the material. So here we are showing that we have a design philosophy which is called as damage tolerant design. That we have these cracks, we have the defects in the material, but what if these are existing? Yet we are able to go for some stipulated time, which is the life of the component, very safely. So nothing is without defects. There will be Schottky defects, there will be Frankel defects, there will be dislocations, there will be, you name it, there will be defects in the material. There will be vacancies in the material and so on. So there are the defects which are existing. But despite these defects being existent, whether there will be some kind of a design philosophy which can handle these defects, and this is called as damage tolerant design. Okay, and this is how the damage tolerant design philosophy started to be investigated by knowing about the level of stress at number of points, by knowing about the type of defects that are existing and so on. You will see, for example, here, this is with respect to time, and there will be some non-destructive type of test which will be done, and you will know about the damage size, how it is going, and you will also know about the repairs that you have to do for a particular piece of material. Okay, so the strength of the material here, though it is not written, you have to know that there will be something called residual strength of the material. So the residual strength of the material is not as great as the virgin material, and therefore there will be some type of trade-off between the defect and the type of load that is coming onto the material, which is decreasing the ability of the material to take further loads. Now, often the student, when I ask them the question, what is the difference between stiffness and strength? He scratches his mind because he has not paid attention to it. Or, here I'm having a figure from one of the books. This is when all as it should be is the first figure A. Okay? Then, if you want to know the stiffness is not good enough, you have that kind of a thing under loads. Some loads have acted and now it has not broken, but some kind of deformation has occurred. And if you want to know more about that, more about stiffness, you will see that, when the people who swim, they go onto that board, they are supposed to take a lift, it gets deformed under plastic deformation conditions, and then he takes a jump. So you will find here the stiffness is not enough. What happens if Young's modulus is too low? Here you have this wing which is broken, not strong enough. This come up. Not enough for fracture toughness. It has fractured now. Okay, somewhere plastic deformation has occurred, somewhere fracture has occurred, and this is how too dense, too high. Okay, you can see that what fracture toughness does. These are different properties or characteristics that this material possesses, which have to be evaluated, which have to be, kind of measured. You have stiffness. This is when we want to know about deformation as far as elastic deformation is concerned. how much resistance is there, and you have Young's modulus, for example. You have strength, which is resistance to plastic deformation. You have yield stress for that. Toughness, you have got resistance to fracture or the energy to fracture. And you have ductility, which is ability to plastically deform or strain to failure and so on. So these types of items are altogether different. What tools we use for fracture toughness determination, we don't use that for strength. What we use for strength, we don't use that for stiffness, and so on. So there are some interwoven things also. Maybe a plot which is generally meant for knowing the strength will give you also the information about stiffness, but not necessarily about the fracture toughness of the material. Okay, so there will be different techniques and different procedures for the determination of those items. Now, approaches of modeling fracture fatigue problems. I have told you that fracture and fatigue is a multi-physics problem. Wherein more than one physical field enhances or degrades the fracture resistance of a given volume of matter. And you have multi-scale modeling, atomic fracture. There is something called peridynamics, as we will proceed. I hope I have written somewhere. And thermomechanical cracking and so on, which will connect with the theme of this topic also. You see, here what we are trying to tell is that you have to look at fracture and fatigue from multi-scale perspectives. That is, you have the, for example, picometers, nanometers, micrometers, millimeters, meters. You have different scales. But what is your way of looking at items is very important. For example, you have an electronic structure. Maybe you have the picometers which are important for this type of an analysis, and there will be tools for measurement of that. Again, that may be subjected, this electronic item may be subjected to fatigue type of modeling, but it will not be in 100 kilonewtons, maybe 0.1 newton, repeatedly. Maybe, temperature boosting by some degree Celsius also combining with this, still we require some mechanical strength of that particular circuitry. And you will see that there is molecular dynamics models, like there is Compton Express, which people can use for determination of how fast the fatigue crack will grow. Okay, so you have different packages which will be able to manipulate the atoms by going to the potential well of that particular structure and so on. And then you have dislocations, and you have, for example, crystals which can be polycrystalline materials and so on. So different scales. And if you have to analyze a structure, maybe finite element may be useful. Not only here, it can be somewhere else also, but the scales will be, of course, different for those type of analysis. And when we talk about quantum field, quantum mechanics is altogether different than continuum mechanics. I hope all of you know about Schrodinger's cat, and you know about that entanglement. You have two cats, both of them cannot be dead, both of them cannot be alive. Schrodinger died long back, but his cats are alive somewhere. So you have to know that what are the rules for quantum mechanics. They're not same in continuum mechanics. And when you combine certain things, you will see that we get peridynamics out of that. So you have this atomistic aspects of fracture. Now herein, if you have high temperature situation, what is happening is that there is also effect of oxygen. You will see that oxygen will also go at the bond places. And what type of oxide? Is it FeO? Is it Fe2O3? Is it Fe3O4? It is also dictated, by the circumstances under which that particular analysis has been done. And therefore, certain things, particularly at high temperature, are altogether different, because you have something like dynamic strain aging which occurs, which I will not be going into the details at this moment. However, those kinds of things do occur, and they do dictate the way we will take a material for usage in nuclear industry. And here you will see, I was talking about peridynamics, and I have tried to give you as short as possible because you don't require it. This will digress me from the actual topic. you'll see that peridynamics is a mathematical thing that unifies mechanics of continuous media, cracks, and discrete particles. So if you have all of these three together, you get peridynamics. You have continuum mechanics, you will use this kind of an approach. You have discrete things, you will use this kind of approach. And you have non-local mechanics, you will see that many of the lectures by, you see, J.N. Reddy. He has written book on finite element analysis, he has written book on continuum mechanics, he has written books on nonlinear finite element analysis. He has also now written, he is about to write, I think, a book on non-local mechanics. I happened to attend one of his courses. So you will see that you use integral things here. And peridynamics is based upon integral equation in contrast to continuum mechanics, which is based on partial differential equations. Thereby, it avoids the partial derivatives which are not defined at discontinuities. Because if you want to find the derivative with respect to x at a discontinuity, you will not be able to find. So those are the kind of, you see, shortcomings with certain analysis which is already available. Now here you will see that you can validate peridynamics and phase field models for certain materials. I have taken one such example from one of the references, and herein we are just look at the last one. Phase field, there are some models which are called phase field models. They give a smaller branching angle and non-physical expansion of damage into the crack surface. So there are certain, shortcomings which peridynamics tries to overcome. Now, having told you about that, I go to now thermomechanical fatigue. So we have a facility by which we are able to go to very elevated temperatures, maybe 600 degrees Celsius, and also to very low temperatures by using some special chambers which have to be, put in enforcement on the machine. Okay, and you will see that here we are showing that there is I square R loss, which is around that particular sample, which has raised its temperature to become red. We say that thermomechanical fatigue and fracture is a combination of thermal and mechanical loads. Okay, so you know the loads by using load cells. You have gotten information how much load you have applied and so on. But if you want to look at the influence of temperature, you have to raise its temperature by a particular, gadgetry which is connected with the machine. Okay, so we are trying to tell here that you have got temperature effects onto the citrus distribution. At the moment, we are not showing you the actual values, but just showing that it is not without reason that the citruses are getting changed because of elevation in temperature. Now you will see here in this particular analysis, after this particular sample was subjected to maybe 600 degrees Celsius, you see you have EBSD type of measurements. I hope you know electron backscattered diffraction patterns that you get, and you have also to compare it finally with something like finite element model, and you can have mesoscale, you can have microscale, and then on the basis of all this, the prediction about the life of a component subject to fatigue is done. Okay, so they are interwoven together, and then we have the ability to tell with certain degree of accuracy what should be the life. So it is a whole long run process. These tests are very involved. They are very costly. No matter you may have material, whatever material preparation, also sample preparation, it is a big deal. But once you have these samples, you have to know that machine has to work for 2 days sometimes. Power should not go. Power backing will be only for 30 minutes. So there are certain nuances with the experiment which are involved, which will be only revealed to you when you visit the lab. So my suggestion to you will be sometime during the program, if you have time, just visit the lab and see how best we have taken the care. I hope that I have some figures which will dictate that what is the complexity, what are the challenges. Okay. and these machines don't run without trouble. Simple, extensometer got damaged. We had to wait for 6 months to get back the extensometer, and they were asking us to pay 5 lakh rupees or something. And you can see so these tests are, they are a dream test, okay? And I don't know how many of you can, afford these kinds of tests. Here, I have tried to tell about the prognostics of high temperature component reliability. As I was telling you earlier about creep deformation or elastic plastic deformation, these get, involved, and you have here in crack formation models, you have crack growth models, and finally, important thing is through measurements, we are able to tell how many cycles have been utilized for growth of the crack from, for example, 10 millimeters to 13 millimeters to 15 millimeters. So we talk about the growth and how fast the growth has happened. Now, this is the type of equipment that is available with us for measurements. So it is a very complicated machine. As you can see, there are hydraulic grips. There is something called load cell. We had to change its oil after probably 1 year, 1.5 years. That was also an involved job. Its filters have to be changed. The oil has to be changed, and so on. So this if this load if this power pack is not there, it cannot run without that. And then there are these hydraulic grips. They have got an independent cooling somewhere here. Okay, so you have to ensure that you have pure, substance which is cooling it. There are filters with this also. This is an independent unit. So means if you have everything which is running nicely, but this is not running nicely, you cannot run the experiment. If this is not running, okay, it is not. So many things have to be checked. Like you are taking off on an aircraft, you check whether this pressure is okay, that temperature is okay, then only you take off. Otherwise, this is a disaster. Okay, so you have got low temperature test chamber is different. Therein we use liquid nitrogen. One liquid nitrogen cylinder is costing us 6,000 rupees. So if we require for a single test 4 these nitrogen cylinders, so you can think that we require 6,000 multiplied by 4 means quarter of a lakh rupees. And then in addition, electricity has not to go. In addition, we have to ensure that if it is for a night, that the pressure does not build up and blows everything up. Okay, so there are many things which come as token problems with a single problem. Okay, and therefore you will find that you have to monitor the pressure on the cylinder continuously, that it is not building up and you are not using it. Okay, so that is for the low temperature. For high temperature case, there is another chamber wherein the sample is loaded and its analysis is being then recorded. For the data is getting recorded in situ, and then you can also look at the data from some other sources. Which there are monitors, which I have not. There is only one monitor at the moment which we have shown here, but you have to look for the readings here and there continuously. So you will see that apparently I have not told you what type of a sample is used, but there are, you have to tell what type of a grip you are going to use. You can have quarter compact tension specimen, you can have half compact tension specimen, you can have full compact tension and middle tension specimen, you can have dog bone sample, you can have flat sample, you can have 3-point bend sample. And these samples, when you use one, so grips also change. And you have to ensure that the material of the grip, if you are using it for elevated temperature, it is having those properties which are expected of that material. If it is not, it is not going to work and everything will be a flop show. And in fact, you will cause more damage to the machine than get anything out of it. Okay. So I have also written fatigue crack propagation is measured by a crack mouth opening technique. There is something called as crack mouth opening displacement technique, CMOD. So we measure that. Okay, and this is high precision crack opening displacement gauge is used with a range of 10 to 12.5 mm with a frequency of 100 hertz. And so you have axial accentometer employed to measure the deformation under fatigue and creep loading. So you will see here in, no, I am giving you a bird's eye view. You can stop me anytime between both, or if you feel that I should not do but more than it is required, I can stop there and then. So we have these types of, test waveforms. You see, you have creep oxidation occurring somewhere. You can see this is here in, you are holding, this is called hold time. So that is how, the creep tests are different. If you want to know what creep is, if you take a big chewing gum and chew it, okay, then you bring it out from your mouth. So it's a bad habit, but I have to explain you like that. So you pull it and keep it, it will go down by its own weight. This is the simplest example of creep. Another example is the shoe that you wear. Okay, it, weight is constant now, but some deformation is occurring, isn't it? Or if you take when this classroom was built, under its own load, it is creeping by maybe 1 millimeter per year, but is going down. No new additional load is kept. Okay, but if we want to know about creep very fast, we have to perform these tests. One creep test may take you 24 hours. You can 24 days. We do not have electricity assurance for 24 days. Now what we do is we go to IG car, okay, which is in China, and we test them for those kinds of experiments. Maybe one of our students will be doing creep tests there. But some limited creep tests are possible here also. And I told you what is the limitation. Limitation is that I cannot ensure the electricity for 24 days together altogether for ensuring that data is not having any kind of spuriousness in its nature. So you have this kind of a specimen geometry. You have to select the strain rate and its amplitude and so on. Now, I gave you many samples, isn't it? Now you have, this is called quarter sample. And this geometry here, we have made it ourselves. This is confidential because I think some of the work has not been published as yet. But the student made some adjustments vis-a-vis the type of facility we have. So this is not available in the market like this. So you have to, three things are very important. If you are doing research, you have to ensure that the material that you are investigating is the material you are interested in. What does it mean? You have to perform XRD. You have to know that this material, if it is 9 chromium 1 moly, it should be 9 chromium 1 moly. It should not be something else. There should be 9% of chromium and 1% of molybdenum in that steel. If it is not, or if it is 304 Allen steel, this 316 Allen steel, these are different materials altogether. And we have to purchase it from some contractor who may not be trusted as such. And you have to know that nobody is going to stop his mill for me. And how much is the production of steel? For example, if you are interested in steel, how much steel is produced in a single hour? Tons and tons. It is having some composition. Now I go to the manufacturer, I tell him, मुझे जी 50 kg चाहिए और ये सर 50 kg के लिए वो कब इसको रोकेगा, कैसे वो परसेंटेज चेंज करेगा? It is like a radioactive decay process that when you give new composition, it will come by that decay process. That full composition that you wanted will be somewhere else. Now how it is done? It is done through secondary type of steel production units, or they go and they use the recycled type of steel, and they enforce the composition that they are interested in, and that's how things go by. But ensuring the composition, that it is having that composition, it is the main difficulty in the beginning, because you will not investigate a material which is already investigated. There is no point in that. This time people are investigating, for example, high entropy alloys, and there are so many high entropy alloys, and you cannot manufacture them in the corner of this inner chute. They require high precision type of those melting type of pots wherein the compositions ensured to be the way we want it to be. So the getting the material in the first place is a big challenge that the researcher himself or herself has to ensure that the material that has been purchased is of the composition which is required. You cannot tailor it subsequently, or the results that you will publish will be, I don't think that any journal will accept it like that. There is any good quality. Then to get this kind of a geometry, you know, you have ADM processes and so on. Again, it requires money. Maybe 5,000 after the material has been obtained. Maybe per sample you have to shell out a big chunk of money for the getting this kind of a sample done. So it is money, money, money. Machines require money. These require money. So you are just watching how the money is going. And you can see here, this is one of the tests which is called by ASTM standards as ASTM E647. It is for the growth rate. I showed you at one place that there was dA by dN. We have some parameter dA by dN versus delta K. So you have to ensure, only this is geometry here. These lines should have been dotted anyway. This is the geometry. Okay. Then in terms of the width, it tells you the dimensions. It tells you certain things you have to do, the notching onto it. You cannot start loading it like this. Even the pre-cracking, if you meet some of my PhD students, they will tell you they were cracked themselves by the pre-cracking. It is a very difficult task. Okay. Sometimes you don't know how many cycles will be required and so on. These are just, this tells you, the crack length is measured as a function of elapsed fatigue cycles. Very nicely written, poetry with it, but the prose is very difficult to understand. And to implement it, it is not only thing is that, you will make a sample without knowing what is the pre-crack, how many cycles you require for pre-crack, then when to stop, how to monitor the data. This will be known to you through visit of the lab only. Okay. Then you see herein again ASTM E647 standard test method for measuring fatigue crack growth rates. You see you have normalized crack size as a function of plane stress elastic compliance, and you have herein this geometry, and you have certain measurements. Certain measurements are possible with us. Other types of measurements for the same quantity using uh, LXT measurements has not been possible because it required another additional 10 lakh rupees or something, which we could not afford. The machine already costs us 2 crore and some lakh rupees. Okay, and plus additionally we had to keep some power pack in terms of power availability for 30 minutes and so on. So that amount was not with us, but we have some other ways of measurement. So this is not directly possible what has been shown. And now you have, for example, crack mouth opening displacement being measured. We are measuring essentially the growth rate dA by dN versus the citrus intensity factor range delta K. This is another parameter. Okay, and you have LVGT type of analysis giving you something. You have here in input of mechanical properties. What does it mean? You see, if you are performing, I showed you thermomechanical type of fatigue. You cannot use Young's modulus, which is recorded at room temperature. If you will see the citrus versus strain graph at 300 degrees Celsius, at 600 degrees Celsius, at 800 degrees Celsius, this will not be same. There will be Young's modulus which will fall by appreciable amount. You will see that the curve goes in and in. And therefore, these property values have to be input to the device, and to the next machine, which is your machine, which is giving you delta K versus dA by dN and so on. So you require these property values. So where from do you get? We get it from, there's another machine, Linus type of see these machine which is meant for stress strain measurements. So you can obtain from UTM, and then put it as an input. So there are measurements at elevated temperatures. Therein also you have to ensure that the strain rate, how much Rajkumar you put the strain rate for the tests for ventilation? So he knows, this strain rate, although people who come there, they will not usually be interested in, they will not know ये किस बला का नाम है, क्यों ये ज़्यादा करना है या कम करना है, but it has got implications on the measurements finding. Herein we have measurement techniques for you will have a strain rosette. Don't confuse it with the same type of strain rosette that you might have witnessed from your 10+2 classes. These are not same strain gauges. They have special materials. They have special bonding, with the type of the loading mechanism. So the cost goes from there. In terms, the principle is probably you have studied the Wheatstone bridge and stuff like that. You have seen that galvanometer reading in your 10+2 class, but it is little bit, advanced in terms of the materials, because it is not to be used for just demonstrative purposes. It has to give us values, and they have to be repeatable, and they have to be reliable. I hope that you know about the uncertainties in measurement. Apart from Heisenberg's uncertainty of delta P, delta X being less than or equal to H upon whatever, but there are some other uncertainties which come in, okay, automatically, and you have to take care of them. So I have explained to you about crack mouth opening displacement, giving you some values which we require. We have linear variable differential transformer, giving you some other values, and we have also a video gauge, which can be used to monitor the type of citrus field near the crack tip. We do not have, there are softwares by which you will be able to convert the strain versus the geometry, you see, in terms of citrus plots and so on, but it is possible, okay, and you can monitor certain things by video gauges as well. Here, this is to just show you how does an extensometer look like. And Mr. Chandrakant to hear me out. When there was trouble with that, how much time did it take us to get it back? Almost 9 months. Almost, I was saying 6 only, so I was, telling them. And we could not do anything. So we cannot take measurement. And probable cause was that we opened the door of the, that chamber, which was very, he wanted to do, experiments fast. So it is ended, so इसको air से तेज cooling करेंगे, उसको oxidize कर दिया, and it is gone. Now you cannot bake. So there are some practical problems, and at least you will know how does an extensometer look like. But I have to tell you that even in USA it was not here. It was deployed in Srinagar. So there are special people who know about the nitty-gritty of the items which are inside. We don't know. For us, it is a black box, and we are users. So we have to use it the way they tell. And you have to, I have already told you that you have this kind of, tension causes resistance to increase, compression causes it to decrease. The same principle is used for measurements broadly. Okay. Now, crack mouth opening displacement, how, this is the sample that you saw. And you have here in this device being connected. So crack tip opening displacement measures displacement near the crack tip. So you can see what type of measurements today are being preferred in the fatigue field. This is the state of art. And you see, hence it provides a direct characterization of crack tip stress and deformation fields. So I have not told you the theory behind it. Then I have to tell you about the Paris law. I have to tell you about the you see the crack this closure phenomena and so on. I have not. I have kept that at lowest level, but I'm trying to only give emphasis on what is being measured, how is it being measured, where the thing is being installed for the measurement, and how that sample was prepared, and so on. So it was first method of fracture toughness measurement. There is another ASTM standard which is called E399, by which we are able to measure the fracture toughness of the material. And fracture toughness is not same toughness that you have studied in your day-to-day courses in your BTech. It is basically having units of megapascal square meter, and it is a critical value of stress intensity factor. So there are methods which are quite repeatable, which have been honored in the circles of engineers. By this method of measurement, we are able to know about what is the fracture toughness of the material. Okay, and this is now recorded in books. So why should this measurement be done again if it's available in books? Because they are new materials, and we want to know about them. What is their fracture toughness? Okay, how are they resilient to fracture and so on? Now here we are telling about compliance, a computer program that controls the interface between the test machine and the compliance system was developed so that the compliance procedure can be carried out to measure the crack length during the adjusted constant amplitude exertion of the marker band load cycles after each block of spectrum loading applied. We have a number of types of loads which we apply. We have something which is called constant amplitude load. We have something which is called as single overload. We have something which is called block overload. We have something which is called random load. We have something which is called aircraft spectrum load and so on. So there are loading patterns which are available in the literature, and with respect to which we want to know that how fast these static cracks are growing. And you will see that there is generally measurement of potential drop in the voltage, and this voltage is proportional to the crack length. That is how you will be able to assess the value of crack length at any instant of time. Now, you have probably known about, I hope that in mechatronics course or in some other measurement course, like there's a book by W on measurements, mechanical measurement W. You will find information on linear variable potential transformer, which is useful, in terms of measurement of items in, if you look at some device like Bowden type of pressure gauge. I hope that you get recalled that how does Bowden type of pressure gauge look like. It has got, first of all, some chamber wherein you have data acquisition system, or you can say that something is getting sensed. Okay, and then you take and you manipulate it. Then you go and transform it. Then you go and display it. So there are some units with every measurement device. You have primary measurements, you have secondary measurements, and you have their transformations so that they become easy to handle. And so this is one such device. I will not go through the details because you might have studied it already, but this is existing in one of the measurement devices in our case. Now in digital image correlation, what is happening is that this technique has got a spectral pattern, okay, before the deformation, and there will be the pattern after the deformation, and you will be able to have an assessment of how much deformation has really occurred under either tension or compression or maybe the cyclic loading. So this is a different principle altogether. Sometimes they use two cameras, sometimes only single camera is used, and so on. And how many frames you are taking per second is also becoming important. We have one such device. You can have a look of this in the lab. So here and also we are showing that the stretch, that rigid particles may not be moving, at all. Flexible particles will move, and this will, the two states are, then you have a reference state, you have a deformed state, and you have got flexible particles versus the rigid particles. So how that behavior is going to be, that is being displayed here. Let's see. Here I am just trying to tell there is also a possibility of acoustic emission testing. And what does it look like, if we use that kind of stuff for the purposes of knowing about the existence of laws and so on. I'm not going to go through details of this. We do not have this directly available with us. Here, thermal imaging, I will tell you, I have used this equipment in IIT Delhi in 1989, in what was called then Industrial Tribology and Maintenance Engineering Center. And they have called it now by another name, I think CAR or something. What is CAR? I think called it now Center for Advanced Tribology or something like that. And you see, I rubbed my foot against the tile, and it has an infrared camera. To focus on this, it will give you isotherms immediately. By this, and you see that in case of certain, boiler tubes, while in human beings will not be directly, assessing the measurement of temperature, this camera is, giving the full scale type of the analysis of temperatures and when to stop the boiler or whether there is scaling and so on. And these papers are well recorded in literature this time. And you will see that you have this based on, actually there is liquid nitrogen, that has to be available there. And this particular thermal imaging, is also useful for certain situations where crack propagation occurs. Okay, we do not have thermography equipment with us, though I hope that the thermal groups or some other faculty member may purchase it. It is a very high, value for welding type of situation and so on. And know about heat affected zone and so on. So here we are showing again back to the crack mouth opening measurements, how these measurements are done. So there are some governing equations also which will be guiding you. And this is crack opening displacement here, and these resistors which were there, which have variable resistances, are able to convert finally the signals into the pattern. This should have been earlier than the thermal imaging, but this has come subsequently. Sorry about that. These are, giving you the location. This is the universal testing machine that I was talking about. It has also got chambers. I think we will go up to 1100 degrees Celsius, if I remember correctly, for this machine. And you have, the possibility also going to low temperatures. How low was that? Minus 70 degrees Celsius. So you can, there are some situations where we are interested in low temperature. There are some situations where high temperatures are required. And, but here also we require liquid nitrogen, isn't it? And you have this as the, specimen, and you know where the extensometer is, but many things will be monitoring from your computer terminal only. Okay, so you have to control the variables by sitting onto the computer. So you will not directly go there and change the parameters. And I was showing you, I had talked to you about these kinds of plots are known to you. But what is important is that if the temperature has risen, this line will shift inside. Okay, and if you rise the temperature further, it will go still in. So you will have the Young's modulus. We have measured it for magnesium alloys. We have measured it for steel. We have measured it for 316, I think, 304 Allen steel, and so on. So we have also the, I think which alloy had been 718, which is the super alloy. Okay, so we have measured that. We have another equipment. You will see this is not anywhere in the North India. No, this is impact tester. It will give you, it will subtract zero point 0.7, I think, kilojoules of energy. 0.7 joules of, huh? Whatever the air friction, it's going to subtract, which otherwise had to be done manually. And there are two types of hammers, I think. One is for Izod type and another is for Sharpie type. So you can have those kinds of testing procedures also, and I hope that it does not take you much time. We will fix some time with them so that they can visit the lab and they can have the first-hand experience of seeing these impact testers. Now, what type of this is from Chandrakant's work on this? With your permission, I'm just showing it confidentially that it was not published. I think as that how this data is then, taken after measurement. You can see you have the scale going up to 300 degrees Celsius, 300 Kelvin. So he has, here in certain values of R square, and he has, plotted impact energy here. And with respect to temperature, how this impact energy is changing. What was the materials which we investigated that time? 304 Ln steel. It's a special steel used in nuclear vessels. Okay, and we have this information. And if you remember, when I started, I showed you nil ductility transition temperature. You can see that the impact energy is falling. As the temperature goes down, the impact energy is falling. And how much it is falling, at what temperature it is falling, and so on, that is only possible by, he has fit some curves to these energy with respect to temperature. Okay, if you give the value of temperature here, you can fix the value of heat. And here, we have a torsion type of tester also in our lab. Okay, you can do torsion type of fatigue also with the specimens. So we have already performed some experiments. The samples for that machine are altogether different than the samples that we normally use for UTM or for the fatigue tester machine. So torsional tests also are possible. So it gives you PR by J type of analysis. It gives you torque. It gives you, what else it gives us? Angle, angle of twist. You can fix that, and so those measurements are also possible. So let us see. You see, you have here in torque, and you have this for length. So it is possible to get those kinds of plots from this machine. Then, after we have performed everything, there is still some measurement to be done on dead body of these samples. If you might have seen, have you visited solid mechanics lab ever somewhere? Have you visited solid mechanics lab? Have you seen any UTM experiment getting conducted? जब इस सैंपल पे लोड पड़ता है ना, ये ऑलमोस्ट कहता है मैं मर गया और इसकी आवाज निकलती नहीं है और टक हो जाता है, यानी रूह चली गई. अब इस पे फिर हमारी बारी आती है पोस्टमार्टम की. So we do the postmortem studies as well on those samples. So how does the postmortem help us? So you can see, for example, you have a typical case which we studied. Okay, you have here in predominant grain boundary decohesion. Okay, we have to show where it is. You can locate it. You can know where are the grain boundaries and how these grain boundaries are. You can use optical microscope. You can use some etchant first. There is some etchant which will etch these particular grain boundaries. It is more selective. It is more harmful at the grain boundaries than at the rest of the grain. And then you will be having an idea that what is going on near the grains. Where are the cracks? Where from they have emanated and so on. How much time I have there? I can continue.
थोड़ा सा start कीजिए ना मैडम.
मैं माइंड अप ही करूँगा
In fact, they can in the coming days they can visit your facility also.
मैं इनको सिर्फ ये बोलना चाहता हूँ आप कुछ ही
Because
चीजें
सर के पास excellent facility है.
आप यहाँ पे
As डायरेक्टर साहब ने बताया था.
ये आप देख सकते हैं यहाँ पे ऑप्टिकल माइक्रोस्कोप के से भी आपको कुछ मिल जाएगा जैसे कि क्रैक कितनी चली कहाँ पे चली मतलब that you will be is it intergranular is it transgranular will be able to know okay these are postmortem studies and then finally I have to thank you
Actually, sir has taught me. He has taught me 3 subjects. I have done my BTech project under the guidance of sir. Am I wrong?
it was excellent so you are now free to ask me you could have asked me in between also so you are free to ask me questions जो भी आपके मानने हैं पूछिए आप पूछ
Maybe in coming days we can visit in your facility. Who the extra facility? वहाँ पे PhD students available. हाँ बोलिए. हाँ.
As you said that young waters is not absolute property. It depends on temperature. How it depends on temperature? How the temperature affects it?
it changes from please take your seat you can take your seat you know things are like this if you have any young modulus or any material let us say steel how much you are taking है ना because this is almost now किसी की बात है आपने कभी ये किसी को क्वेश्चन किया कि इसका 210 क्यों है 198 क्यों नहीं है 215 क्यों नहीं है ये एक्सपेरिमेंटल वैल्यू है ये है स्लोप सिट्रस स्ट्रेन कर्व का यही सिट्रस स्ट्रेन कर्व चेंज होती है टेम्परेचर के साथ किस मटेरियल को कितनी उल्टी आएगी ये हमें पता नहीं है कौन कितना स्ट्रांग होगा ये हमें बिल्कुल खबर नहीं है हमें एक्चुअल मेजरमेंट्स करने पड़ते हैं और जैसे ही उसकी कर्व जब भी बनती है वो ऐसी होती है कि क्या हम उस मोड में जा सकते हैं जहाँ पे मैं लिख सकता हूँ कुछ लेट मी एक्सप्लेन हाँ हाँ से ये पेन है ये मान लीजिए ये सिट्रस है नो प्रॉब्लम ये आपकी रूम टेम्परेचर वाली कर्व है ना अब आपने 200 डिग्री पे किया ये आई 300 पे किया ये आई 400 पे किया ये आई ये जो है ना यहाँ पे इसका स्लोप ये चेंज होता जाएगा एंड मटेरियल इज बिकमिंग मोर कंप्लायंट ई इज फॉलिंग आप मान लीजिए सीढ़ी है कहीं पे वो ऐसे है वो तो बहुत तगड़ी सीढ़ी है थोड़ा कीजिए ये चढ़ सकते हैं और बच्चा भी चढ़ सकता है ये तो बिल्कुल ही कुछ नहीं तो ये मतलब इसकी स्टिफनेस ही खत्म हो जाती है लगभग विद इंक्रीजिंग टेम्परेचर वर्ल्ड ट्रेड सेंटर कैसे फेल हुआ क्योंकि वो मेल्टिंग पॉइंट के करीब पहुंच गया तो उसका जो ई है वो तो बहुत ही कंप्लायंट बन गया उसकी कंप्लायंस इंक्रीज हो गई स्टिफनेस डिक्रीज हो गई so this is that it is by actual measurement so the answer to the question is Young's modulus is determined as a function of temperature for the purposes of usage and analysis you can have a material and you can determine the values of Young's modulus at 4 or 5 different temperatures then you may be able to fit the curve that for example you are saying that this is now the temperature and this is Young's modulus it was at room temperature it had some value here at 100 degrees Celsius it has some value at 200 it has 3 so you may be able to fit a curve but it will be true only for that material of that composition but in between still there will be suppose you have this was at you see 20 degrees Celsius this is at 100 degrees Celsius suppose you have it at 80 degrees Celsius you have no two values you may be able to manipulate those values but it's not something which is already in books you will find most often they give values at room temperature and maybe some temperature of interest to a researcher ठीक है बताइए हाँ वो तो डिफरेंस फिनोमेना है ऑल टुगेदर जो आप कह रहे हैं ना, मतलब हमारी वो एक और है वो एनर्जी है वर्सेस टेम्परेचर। तो ये ऐसे जाती है, इसको बोलते हैं यहाँ पे, ये जो टेम्परेचर है जहाँ पे होती है इसको बोलते हैं मिल्क डक्टिलिटी ट्रांजिशन टेम्परेचर। वो यहाँ से ये डक्टाइल है, यहाँ से ये ब्रिटल है, वो डिफरेंट मेजरमेंट से आपको मिलेगा। दैट विल नॉट बी गॉट फ्रॉम द सेम एनालिसिस।
Sir, what are the different techniques to measure the flaws of the material, sir?
Huh?
Different techniques to
For-
measure the flaw or crack on the material. That means surface of the material or internal of the material.
आप तशरीफ रखिए, मैं तो कोशिश करूंगा आपके सवाल के जवाब का। आप देख लीजिए कि जो हमारे पास टेक्निक्स है कुछ तो है, उनको डाई पेनिट्रेंट टेस्ट करता है, किसी को हम बोलते हैं कि एडी करंट टेस्ट, और भी कुछ मैग्नेटिक पार्टिकल टेस्टिंग भी है, कुछ मतलब उनको बोलते हैं हम नॉन डिस्ट्रक्टिव टेस्ट। उससे आपको इनिशियल फ्लॉ साइज के बारे में एक्चुअल जो हमारा कमर्शियल ये कंपोनेंट है उसके मिल सकता है। लेकिन जो हमारी टेस्टिंग प्रोसीजर्स यहाँ पे है उसमें हम इंटेंशनली क्रैक को रखते हैं किसी जगह पे, फिर हमारे पास मोड्स ऑफ लोडिंग होती है। हमारे पास मोड 1 टाइप ऑफ लोडिंग है, मोड 2 है, मोड 3 है। जल्दी हम मोड 1 में उसको लोड करते हैं और उसका देखते हैं बिहेवियर इन टर्म्स ऑफ क्रैक लेंथ कितनी आगे बढ़ेगी। लेकिन जो इनिशियल फ्लॉ साइज है नॉन डिस्ट्रक्टिव टेस्ट के कारण हम कुछ कुछ के बारे में बता सकते हैं, लेकिन अगर कोई नैनो स्केल पे है वो हम एकदम नहीं बता सकते हैं। लेकिन टेस्ट के थ्रू वी कैन नो व्हाट इज कॉल्ड एज थ्रेशोल्ड वैल्यू ऑफ द सिट्रस इंटेंसिटी फैक्टर। कि जब हम ये प्लॉट्स बनाते हैं, जैसे हमारे पास DA/DN वर्सेस डेल्टा के है, तो यहाँ पे के जो पोर्शन है, यहाँ पे ये कितने डेल्टा के पे ये क्रैक इनिशिएट शुरू होना जाएगी, उसको हम बोलते हैं थ्रेशोल्ड वैल्यू। वहां से हम बता सकते हैं कि ये क्रैक जो है कितनी है क्या नहीं। बाकी जो हमारे पास डिफेक्ट्स हैं, या तो वैकेंसी डिफेक्ट्स होते हैं, या हमारे पास डिस्लोकेशंस होती हैं, या हमारे पास फ्रैंकल डिफेक्ट होता है, या फ्रैंक रीड सोर्स होता है जहाँ पे जितने आपको मर्जी है उतने आपको डिस्लोकेशंस मिल सकती हैं। तो ये बात है, ठीक है।
सर,
हाँ।
मेरा एक सवाल था कि अभी आप कह रहे हैं जो डिफेक्ट्स हैं कभी-कभी कुछ होते हैं।
हाँ।
कोई रियल लाइफ एग्जांपल है?
हाँ, जब तक अंडे में वो क्रैक नहीं हो जाएगी तो कोई फूड तो बाहर नहीं निकलेगा। ये तो सेकंड में बताता हूँ। आपने देखा होगा जो कैलीग्राफर्स के पेन होते हैं ना, उनमें क्रैक लगाई जाती है, पीछे आती है। तो ये तो है मतलब, और मतलब ये तो आपको मतलब यही दो एग्जांपल मुझे जहन में इस वक्त आ रही है। आई होप आई हैव आंसर्ड योर क्वेश्चन। और बताइए। कोई और सवाल है?
सर और क्या है, तो जैसे कि आपकी टॉपिक बहुत इंटरेस्टेड है सर, कोई करना चाहेगा अगर आपके टॉपिक पे, तो वो तो पहले ही डर जाएगा जो टर्म्स एंड कंडीशंस।
नहीं ऐसा बात नहीं है,
सब जगह ऐसी हो
यार ये हर जगह don't think कि life is a bed of roses for anybody. This is very difficult. आप जहाँ जहाँ कौन है वहाँ से ये दामन बचाना है तो चलना है। हम भी यही करते हैं। अगर वैसे हम कहेंगे ना तो फिर कोई चांद पे तो सोच ही नहीं सकता है जाने का। There will be failures. You know, life's battles are not won always by the strong people, but by the people who think they can. You have to go and say that I can do it. वैसी बात नहीं है, फिर रास्ते निकलते हैं। आप इस इंस्टीट्यूट में तो पहले से नहीं थे। अगर आपको पता होगा ना, यहाँ पे अगर सुई खरीदनी होती थी उस पे 17,000 फाइल्स चलती थी और वापस आता था कि नहीं इसको जुर्माना करो। अगर मैंने वैसा सोचा होता तो मैं तो पता नहीं मेरी कबर पे कब तक घास आया होता। वैसे थोड़ी है। You have to go and face the light. You are young, you are energetic. Lab is there. If 4 or 5 people have been able to do, You can ask Chandrakant and that Ashutosh how difficult it was. ये तो पता नहीं कितनी बार क्या क्या सोचे मेरे बारे में, ठीक है ना, मतलब ये कहीं पे लाइफ इज नॉट अ बेड ऑफ रोजेस, एंड इफ वन ह्यूमन बीइंग कैन डू समथिंग, बी एश्योर्ड दैट एनी अदर ह्यूमन बीइंग कैन डू। ऊपर वाले ने जो अंतर रखा है, अल्बर्ट आइंस्टाइन जैसे बहुत कम होते हैं, बाकी हम सब एवरेज लेवल के। अगर मैं कर पाया, आप से नहीं कर। हाँ, और कोई क्वेश्चन है?
Sir, what is the effect of you told about effect of oxygen in Dept propagation? I could not get that.
Actually,
Yes, sir.
actually, what is happening is that oxidation process. It is also, in a way, causing what is called as dynamic strain aging in the material. It's a different phenomena. It is not generally studied at Dept level. You can, in simple terms, think that there was a surface which had nothing on it. But now that oxygen molecules have decided to come, and they may react chemically, or they may sit there, and obviously, near the tip of the crack, they will influence its behavior. Because crack tip sharpening and blunting is occurring, by the use of a variable type of loading. You have cyclic loads which come. You have maximum load, you have minimum load, you have maximum load, minimum load, and that is what is causing the material to behave in a special way, and which is not as far as the endurance limit of the material is concerned. If endurance limit of the material was the prime criteria, things would be just elastic, 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 and they will be, what is called as having zero type of tolerance for the plastic deformation. But practically, you have this plastic deformation, you have oxygen coming into play, you have type of oxide, you have Fe2O3, I told you, for iron type of situation, or if you have FeO, or if you have Fe3O4, all of them have got different, behavior, and they, by attacking the material at molecular level, they cause damage in a very subtle way. But this is not the complete answer to dynamic strain aging. I can discuss with you sometime else. Okay. Any other question?
So let us thank sir for giving me
Thank you so much, sir, for such an informative and lively lecture today. So thank you all of you for being such an amazing and a patient audience. Now I'd like to announce that we will be going to HPCL bottling plant at Pampur. So I request all of you to proceed towards the main building fountain. Koshan here will be leading the way. We will be leaving in the college buses from there, and lunch will be served at the venue. Thank you so much.
so we have packed lunch for you all.